So question 3a part 1, they want you to define standard electrode potential. So standard electrode potential, or the way we pronounce this as E0, is the potential difference. So you're looking at whatever your system is. So this is relative to a standard hydrogen electrode. So everything in the data booklet is referring relative to the standard hydrogen electrode, which has a relative value of 0.00 volt. So by default, this is between a standard hydrogen electrode and a metal. Basically the electrode. In the case of a non-metal, you will have a metal as an electrode, which is typically platinum as your inert electrode, which is why it's between that and a metal, which is immersed in a solution, and this solution containing the ions. I don't want to say metal, I just want to say the containing the ions, and this is at 1.00 mole per dn cube concentration, 298 Kelvin or 25 degrees Celsius, and also 1 atm pressure. So these are the standard conditions as required by the definitions as part of that standard thing there. Anyway, so we have the next part of the questions. We have 3 redox systems. What do they want us to do? They want us to complete the table by adding the labels A, B, and C to deduce the order of E0 for the 3 half cells. How do we decide this? Okay, so looking at what you have, okay, so if I just very quickly scribble out what we have. Nope, I don't want that. Nope, I really don't want that. Okay, never mind. I'll just draw it like that and that, and then we have the salt bridge, and then obviously we have a platinum and a voltmeter going like that. We have a plus, we have a minus electrode there. What we have here is obviously is a lot easier with your diagram in front of you, but obviously with the question paper not in front of me, the best I can do is show this in this context for you, and hopefully after I explain this first bit, then the second bit will be easy peasy lemon squeezy for you. So we're comparing the movement of electrons from one system of equilibrium containing the 2 complexes to the other one. Judging at this, if this is negative electrode and this is positive electrode, so what I can say is electrons are negatively charged, and it is electrons that are moving in a cell. So in a cell you have electrons moving. Electrons are negatively charged, they flow towards the positive terminal. Positive terminal is what you call anode. So electrons are coming, am I correct? Electrons are flowing here. This is the positive electrode because it's the opposite charge there. So this is the anode. Okay. So this is the electrode at which you gain electrons. So reduction happen here. If reduction happens there, this means this is the E rad. So therefore we can say that this is more positive value, more positive E rad compares to this, because the electrons like to come here, and this is where reduction happened. So this goes from right to left. So this has more positive E0. In your diagram, in your table that you're supposed to fill in for part 2, you're given it in terms of negative. So instead of thinking about more positive, I can think about it as less negative. Okay, so more positive means less negative. So let's say this is system number 1, this is system number 2. Then system number 1 is less negative than system number 2. Better don't use that numbering system. So what I have to do now is I can just complete these and paste it for the other system. Hopefully it will be clear for you as well. So let's see what we have on the other side. So what we have on the other side is something similar, but then we move these complexes around. So I have the En complex on that side. Instead of ammonia, I have water as my ligand on the left hand side now. This is still plus, this is still minus, so the electrons still like to move towards the positive terminal, so electrons go there. Electrons are negatively charged, they flow towards the positive terminal. Electrons like to come here because this is where reduction happened, so reduction happens here. Therefore this is the E-red, therefore this is more positive, or I can think about it being less negative. And if that is less negative, then the ruthenium, sorry, that should be En3, there should be En3 as well. Okay, so if that is the case there, so if this is less negative than that, and this is less negative than that, so ultimately we can fill in our table from the most negative to the least negative. We are just looking at redox system, redox system A, B, or C. So this thing here, this is redox system C, and this is redox system B, and this is redox system C, this is redox system A. So A is the least negative because it's less negative than that, and that is less negative than B. So the least negative is going to be A, and the most negative is going to be B, and C just lies somewhere in between, just like that. And there's 1 mark for a lot of explanations, but because they're not asking for explanations, it's just the way you think about it in terms of where the electrons are moving. The key really is based on this plus and minus given in the respective questions. So to the next part of this question, still on question A, but this is part 3. This is now stereoisomerism, and you have bidentate ligands, so you can just show them like that. What we have is we have ruthenium En3, 3 plus, so we have 3 times of the same bidentate ligand. This is the recipe for getting specifically optical isomerism. So they already told you it's stereoisomerism. They want you to name the type of isomerism. So the type is going to be optical isomerism there. And in terms of drawing it, I need to draw mirror images because there will be none super impossible. So I gotta draw 3-dimensional mirror images. I know that it's a 3-time bidentate ligand, and they told me that I can draw it like that, and like that, and like that. So don't forget the charges in a square bracket. So that is just what I normally do. I don't know whether the examiner will penalize you or not, but it's a very common thing for transition metal chemists like myself. We always draw a bracket and then put a charge outside like that. So we have a mirror plane that we have to draw the mirror images of this thing. So before you draw mirror images, put in all the 6 coordination sites that you have in the octahedral complex. So these 2 are flat, just like these 2 are flat in the plane, in the screen or in the paper that you're writing on. These 2 are pointing away from you. These are 3-dimensional diagram, away from you, behind the screen, behind the paper. These 2 are coming up from the screen, from the paper, pointing towards you. So I put in all my nitrogen again. And I know this is a mirror image. I draw 1, so this will mirror project itself onto that side. So this project it onto here, this will project it onto there, and last but not least, this will project it onto the other side, like that. Okay. And of course, put in the charges as well, just as you would for the complex that you are drawing. So for the 3 marks, you get 1 mark there, 1 mark there, and 1 mark for being able to get is optical isomerism there. So question 3, part B. What do you have? You have a Br2 and Br minus. So if I write down these things straight from the data booklet, so you should be looking for alphabetical order. The way we write this is showing reduction, because everything in the data booklet is showing you reduction potential. Let me just open up my data booklet. So alphabetical order, the silver plus and silver, that is plus 0.80 volt. the bromine is plus 1.07 volt. So this is the more positive, E naught. Therefore, it is where reduction will happen. Where reduction happens means you will gain electrons here. Okay, so the electrons, the electrons come to this particular electrode. If I draw it, that means the electrons go from there to there. These are movement of electrons because reduction happens here, oxidation happens there. And if electrons come here, electrons are negatively charged, so this thing will be positive terminal and this thing will be negative terminal. You're not doing electrolysis. This is electrode cell potential. So E cell is going to be E red minus E ox. Not the other way around. E red minus E ox. So this method means I just need to read the value straight from the data booklet. The more positive one is the E red, so it's plus 1.07 minus bracket plus 0.80. Put it into the calculator. 1.07 minus 0.80. So your calculator will not show you the plus, but as with anything with physical chemistry, sign, value, and units is a must. Alright, as all the values given in the data booklet, they all have a plus when it's positive. Your calculator will not be able to think for you, so you need to think for yourself. So the direction of electron flow is going to go from the silver plus silver system towards the Br to Br minus system. As a result of what I've said earlier, you are not doing electrolysis. This is a result of cell potential. Now question 3b part 2. This is about changing to non-standard conditions. So far, everything you've done straight from the data booklet, those are all standard electrode potentials. So meaning all of them are under standard conditions. Meaning to say originally your E naught silver plus silver, which I have written above, it was plus 0.80 volt straight from your data booklet. So plus 0.80 volt is at 1.00 mole per dm cube. Let me just improve the handwriting a little bit. This is for silver plus electrons going to silver as shown in your data booklet. And we know that this was your E-ox. It was your E-ox just now. So that is your E-ox. What can we say? Okay, it's better if I explain first because it will make more sense. This is basically a qualitative explanation in terms of Le-Chatelier principle based on this equilibrium. So for the Ag plus electrons going to Ag equilibrium, when you add water, when water is added, so you are diluting the concentration, so Ag plus falls below the standard 1.00 mole per dm cube. This is standard condition. So what happened then is the equilibrium will try to increase, to do the opposite. It will try to increase the concentration of Ag plus, because here the Ag plus concentration decrease. The equilibrium will shift in order to increase the concentration of Ag plus. The equilibrium will try to increase Ag plus by shifting to the left. When you shift more to the left, this E naught will become less positive. Therefore, it's no longer E naught because it's no longer under standard condition. So I don't write the E naught anymore. I just write E, Ag plus or Ag less positive, then plus 0.80 volt. And this is your E-ox. So just now, if this become less positive, then this 1.07 minus something which is less positive, this will become more positive. So this one will become greater than plus 0.27. Therefore, E cell becomes more positive as you are taking away the EOX, which become less positive. So I don't really need to write this last statement. In fact, it was just a tick in the box. So it was less positive, it was no change, and the other one is more positive. So among the three changes, I will get more positive as a result of taking away something which becomes smaller. So as this thing becomes smaller, something positive minus something smaller, less positive, will become more positive. So this is just the idea on Nernst equation, but without really writing down the expression for Nernst equation. This is the qualitative explanation based on Lee-Chatelier principle. Question 3, part C. They ask you to define the term ligand. So you always get free definition here and there. Ligands refers to molecules, or in fact it could be ions. So ions, it must have at least one lone pair. You could have more than one lone pair of electrons, but you must have at least one lone pair of electrons. And what does this lone pair electrons do? It forms dative covalent bond, or it forms coordinate bond, whichever one you like. Just stick with one, and this is to a metal ion center. Not necessarily metal ion, but most of the time it's metal ion. What we have is Kc. They are not asking for K step, so we have a Kc. And looking at the expression that you have the silver, and you have S2O3 twice. So there's two ligands on the silver plus, because each of these is S2O3 2 minus. So you got S2O3 2 minus, S2O3 2 minus, and you got one Ag plus, minus 4 plus 1 equal to minus 3. What am I talking about? That's how you get the minus 3 charge overall. Don't forget, this is how you write for the expression of a complex. For Kc, you need equilibrium concentration. So I put another square bracket for the concentration. The power is 1, because in front of the balance equation, which you have on your question paper, is just 1 of the silver. Okay, I think as a matter of fact, I might just write down the equation here, because it's quite an important thing to do this in the context of having the questions. So AgBr plus 2S2O3, 2 minus in equilibrium, giving you AgS2O3 twice, and then 3 minus, as I mentioned about the charges. What is important is also the stat symbol, because the stat symbol will govern you what will appear in the Kc expression or not. This is a solid, so concentration of unity is taken. Unity meaning concentration of just 1. The value is given as 1 rather than 0, so that you can still do the calculation whatsoever for the rest of your expression instead of setting it to 0. So the top bit, they are both to the power of 1, but this bottom bit is to the power of 2. As you see in the balance equations, there are 2 S2O3 2 minus in the expression, so it's squared there. And sometimes they ask for the units, but here obviously mole per dm cube times mole per dm cube is mole per dm cube 2 times, and you also have mole per dm cube 2 times. There's actually no unit for this particular expression. Question 3, C part 3. So we're given KSP and we are given K step. So we need to use these answers to calculate Kc for equilibrium 1 and include the units. So what do we know about K step? If we look at this expression, we can tell that K step, what am I looking at? K step as well as solubility products. Let's talk about solubility product first of all. So we have AgBr going to Ag plus aqueous plus Br minus aqueous. Okay, so that is your KSP. I should really draw an equilibrium. In terms of K step, is relative to the aqueous complex. So what I have is 2S2O3 2 minus in equilibrium to give me AgS2O3 twice, Ag plus 1, and then minus 2 times 2 is minus 4. That's how I get it, it's 3 minus. Plus of course the water molecules that I kick out, so I'm not writing how many water molecules I have there. This is just a simplified expression to show for the what am I talking about for this second one, which is K step. So my KSP is equal to concentration of Ag plus time concentration of Br minus above to the power of 1 according to this expression following the solubilizing the silver bromide like that. And from here our K step is going to be the concentration of AgS2O3 twice 3 minus, don't forget concentration in a big square bracket, divided by the concentration of the Ag plus aqueous as well as S2O3 2 minus square. So use this answer to show what is going on. I have Ag plus there, I have Ag plus there. Obviously, they are not going to be required somehow because there's no Ag plus concentration in there. So I need to try and relate these two together. I can see this thing is on top. So I also got Br minus on top. So it has to be K step times KSP. Then the Ag plus and Ag plus cancel. I get this at the bottom. So I hope you can see that this is on top, this is on top. So K step must be on top. And it has to be multiplied by KSP since I want Br minus on top as well. It has to be this multiplied by that. So that's how easy it is to get the expressions. So Kc above, meaning this thing, is obtained by multiplying KSP time K step, and you could see that because you know the definition for each of these. And based on this value, therefore my Kc is equal to 5.4 times 10 to the power minus 13 times K step, which is 2.9 times 10 to the power 13. Include the units for Kc. Okay, so previously I already told you about the units there. So it was mole per dm cube times mole per dm cube divided by mole per dm cube, the whole thing square. So obviously you could see here that there are 2 lots of mole per dm cube, and that cancel out the whole thing, and that's why you will not get any unit, and in your final answer you will just say no units. So let's do this on our calculator. So I get 15.66. However, given the data which was to two significant figure back in AS topic 1, they already said that candidate should be able to understand what is appropriate number of significant figure based on the data given. So this is Kc, I am giving it to 2 significant figure based on what is appropriate amount of data, what is appropriate significant figure based on the data given. Next up, so part D, which is the last 2 marks of this question. So question 3, part D, I have stability constant, and actually the previous K step was given, was it? Yep, because the AgS2O3 2 minus, so the whole complex is 3 minus. The K step value is given above as 2.9 times 10 to the 13, whereas silver with 2 Cn minus, and that is 5.3 times 10 to the 18. And next, last but not least, I have the silver diamine complex, which give me that. And deduce the relative concentration present in the resulting mixture. So hopefully not looking at the value in front, but rather looking at the powers of 10. This is 10 to the 7th. This is the smallest because it's 10 to the power 7th. This is the biggest, is 10 to the power of 18th. The bigger the K step, the more stable is the complex. The more stable is the complex, the more of these you will have in equilibrium. Therefore, in terms of highest concentration, you will have silver with the 2 Cn minus. So this is going to be highest, followed by the second highest, which is the silver with S2O3 2 minus, as given in the data above. And then this one is the smallest, comparing all 3. So silver with 2 ammonia and a plus. Now they ask you to explain, so highest K step value would imply the more stable complex. Highest K step value implies AgCN twice minus is the most stable complex, and if it's the most stable complex out of the 3, therefore present in largest concentrations. And having said that, the one with the smallest K step will obviously be present in the smallest concentration, or in the question they said lowest concentration. That was how they label it. Okay, so that's the end of that 15-mark question number 3.